He was the man Albert Einstein worshipped as a god, a genius, whose funeral literally stopped an entire nation. Yet, despite authoring the mathematical architecture of the future, he spent his entire life stubbornly defending a scientific ghost. It remains one of the most compelling, heartbreaking paradoxes in the history of science. The very man whose equations made the modern world possible, from the GPS in your phone to the lasers in our laboratories, anchored his entire philosophy in a reality that did not exist. Welcome to Legendary Lives Unveiled. If you are drawn to the hidden tragedies, the bitter rivalries, and the profound psychological depths of history's greatest minds, I urge you to like, share, and subscribe to our channel as we continue to unlock the archives of the past. Today, we confront a massive stack of historical paper, pulling from the extensive biographical research of historians Fritz Behrens and Dirk van Delft, original translated correspondence between the greatest physicists of the 20th century, and the dense civil engineering reports from a 1920s Dutch state committee. Our mission is to synthesize this monumental archive to understand the intellect, the life, and the deep contradictions of Hendrik Lorentz. He was sitting at the absolute epicenter of the transition from classical physics to modern quantum mechanics. But the image Lorentz projected to his peers, to the world, was a meticulously constructed facade. To the scientific community, he was Mr. Perfect. He was an incredibly polished, polyglot genius who chaired grueling international conferences with effortless grace. He operated with a serene, almost Victorian detachment, never seeming to break a sweat. But beneath that pristine exterior, the biographical data reveals a man forged in an environment of extreme, suffocating instability and relentless trauma. Hendrik Lorentz was not born into academic royalty. He was born in Arnhem, in the Netherlands in 1853, into a reality defined by economic anxiety and devastating loss. The historical context of 1850s Arnhem is absolutely crucial. His father, Gerrit Frederick Lorentz, originally owned a nursery, but the records show Gerrit suffered from a game leg, a chronic physical disability. In a mid-19th century agrarian economy, lacking physical mobility was a virtual economic death sentence. You simply could not maintain a nursery if you could not walk the grounds and endure the grueling physical labor. This triggered a forced, desperate economic pivot. The father had to abandon the earth. He tried his hand at carpentry, a trade requiring immense physical stamina, and that failed to sustain them. Finally, he opened a grocery store, which the historical records show he essentially ran into the ground. The business completely collapsed. From the literal moment Lorentz took his first breath, his household operated under the crushing, omnipresent stress of impending financial ruin, and that economic terror was immediately compounded by a profound, incomprehensible personal tragedy. When Hendrik Lorentz was just 4 years old, his family structure disintegrated entirely. The timeline detailed in Van Delft's research is staggering. First, Hendrik's 3-year-old brother died. Then, a mere 6 weeks later, his mother, Gertrude, passed away. A 4-year-old child, losing his primary sibling and his mother within a month and a half. The upheaval did not stop there. Just 6 months later, his father remarried a woman named Luberta. From a developmental psychology standpoint, this young boy experienced a catastrophic collapse of his foundational reality. His primary caregivers vanished into the earth. A new maternal figure was introduced almost instantly, and the underlying financial anxiety of the failing grocery store never faded. His physical and emotional world was entirely unpredictable. It was chaotic. It was dangerous. When we examine his later academic pursuits with this specific childhood trauma in mind, the correlation is impossible to ignore. He dedicated his entire existence to theoretical physics. to finding the absolute, immutable, rigid laws of the universe. It reads as a profound psychological defense mechanism, a superhero origin story born from grief. The human world had failed him. It took away his family. It offered zero security. So, he sought out a reality written purely in mathematics. He desperately needed an environment where things actually made sense, a universe governed by unbreakable rules. The archival evidence frames his lifelong obsessive attachment to classical physics not merely as an intellectual stance, but as a psychological necessity. Classical physics is deterministic. If you know the initial conditions, you can calculate the outcome with absolute, unwavering certainty. For a mind forged in trauma, that predictability is a sanctuary. This interpretation sheds blinding light on his lifelong devotion to his primary school headmaster, a man named Timur. The sources highlight Timur as the great catalyst. Timur recognized this quiet, gifted child and introduced him to advanced mathematics and the physical sciences. He wasn't just teaching Lorentz numbers. He was handing a traumatized boy the keys to an ordered universe. In the realm of mathematics, equations balance perfectly. There are no sudden illnesses. There are no collapsing businesses. There is no grief. There is only logic. Timur provided the framework that allowed Lorentz to impose order on his terrifying reality. And Lorentz maintained a deep, enduring gratitude toward him for the rest of his life. Lorentz's drive to master this new, ordered world became relentless, almost mechanical in its intensity. There is a specific anecdote in the biographical files that perfectly highlights this terrifying focus. Lorentz was raised in a Protestant environment, and as an adult, he was known as a highly secular freethinker, entirely driven by empiricism. Yet, as a young boy, the records show he regularly attended Catholic Mass in his local town. His motivation for attending was utterly devoid of theology. He realized that the local Catholic Church conducted its services in French, so the boy sat through Mass on a weekly basis, purely to optimize his linguistic skills. He utilized the religious infrastructure of his town as a free language laboratory to practice his French comprehension. The sheer pragmatism of a child that age is astounding. That intense drive propelled him through the educational system at a velocity the Dutch academic establishment had never witnessed. He entered Leiden University at age 17. He secured his bachelor's degree in mathematics and physics in a single year, graduating at 18. By 22, he completed his doctoral thesis. And because he was entirely self-made, he paid his own way through this exhausting doctoral research by teaching night school in Arnhem. But we must pause to examine the sheer substance of that 1875 doctoral thesis, because it was a masterpiece of theoretical deduction. At the time, James Clerk Maxwell's theory of electromagnetism had only recently been published. Maxwell proposed that light, electricity, and magnetism were all manifestations of the same phenomenon, traveling as waves through invisible fields. It was highly complex mathematics, and much of the established scientific community viewed it with deep, entrenched skepticism. They were not sold on it, but Lorentz, in his early 20s, took Maxwell's controversial equations and applied them to the physical boundaries of different media. He mathematically explained the reflection and refraction of light with flawless precision. He took a highly abstract theory that senior scientists distrusted and proved it worked in the physical world using pure math. The academic establishment immediately realized what they had on their hands. In 1878, at the age of just 25, Lorentz was appointed to a full professorship. He was given the newly established chair of theoretical physics at Leiden University. The historical significance of that specific title, Chair of Theoretical Physics, cannot be overstated. Originally, the post was offered to Johannes Sanderdaels, renowned for his work on gases, but he took a position in Amsterdam. So, Leyden handed it to the 25-year-old Lorentz. Prior to this moment, physics was almost exclusively a hands-on, experimental discipline. The dominant figures in Dutch science, men like Huyck, Kamerlingh, and Ons, were experimentalists. They built vacuum tubes. They operated massive magnets. They got their hands dirty recording temperatures. The very idea of sitting at a desk, deriving differential equations on a piece of paper, and calling that physics, was considered highly unorthodox. The experimentalists viewed theoreticians as mere philosophers, completely divorced from the tangible realities of the laboratory. By establishing this chair, Leiden University formally recognized that the mathematical mapping of the universe was a distinct, essential, and equally valid branch of science. Lorentz legitimized the entire profession. He demonstrated that rigorous mathematics could predict reality before the experimentalists could even build the machines to measure it. This absolute mastery culminated in 1892, when he developed his theory of electrons purely through mathematical deduction. He bridged a massive looming gap in 19th century physics. Maxwell's equations described electromagnetism as continuous fields, smooth, uninterrupted waves of energy. But the chemistry of the time, building on the work of John Dalton, strongly suggested that matter was discrete, made of individual, chunky atoms. Lorentz asked the critical question, how do continuous electromagnetic fields interact with discrete solid matter? He looked at the math of both systems and concluded there had to be a physical intermediary. He postulated that inside these atoms, there must be infinitesimally small, discrete particles carrying a negative electrical charge. He theorized that the vibration, or oscillation, of these charged particles generated the electromagnetic waves we perceive as light. He fundamentally proposed the underlying structure of matter. Years before J.J. Thomson physically isolated the electron in a cathode ray tube experiment in 1897. He predicted the particle before human eyes ever saw it. And he didn't stop at mere prediction. He used his mathematical model to solve actual experimental mysteries in real time. In 1896, he collaborated with his former student Peter Zeeman. Zeeman was conducting experiments where he placed a light source, a sodium flame, between the poles of a massive, powerful electromagnet. Looking through a spectrometer, Zeeman noticed something bizarre. The distinct spectral lines of the sodium light, which should be singular and sharp, were actually splitting into multiple distinct lines when the magnetic field was activated. Zeeman observed the phenomenon, but lacked the theoretical framework to explain it. He presented his findings to Lorentz. Instantly, Lorentz applied his discrete particle theory. He reasoned that if light is produced by vibrating charged particles inside the atom, and you subject them to a strong external magnetic field, the magnetic force will alter their trajectories. The magnetic field accelerates particles vibrating in certain directions and retards those in others, altering the frequency of the emitted light. That altered frequency was exactly what Zeeman was seeing as split spectral lines. This mechanism is what we now call the Lorentz force, the specific force exerted by both electric and magnetic fields on a point charge. Lorentz used Zeeman's data to calculate the exact charge-to-mass ratio of these invisible particles, proving mathematically that they were thousands of times lighter than a hydrogen atom. It was a flawless synthesis of theoretical prediction and experimental verification, earning them both the Nobel Prize in Physics in 1902. He was mapping the subatomic structure of the universe with a pencil, and his calculations perfectly predicted laboratory reality. He had established his absolute, undeniable genius, but as we dig deeper into the historical archives, a terrifying, massive contradiction begins to emerge. He was defining the fundamental particles of the modern world, yet his entire theoretical architecture rested on a foundation that we now know to be completely fictitious. He was absolutely obsessed with the luminiferous ether. Why would a mind capable of predicting the electron stubbornly cling to a 19th century ghost? To comprehend his absolute attachment to this phantom medium, we must violently strip away a century of modern physics. We must view the universe through the strict epistemological framework of the late 1800s. At that time, human understanding of wave mechanics was strictly mechanical. If you observe a water wave in a pool, the energy is moving, but the water itself is the physical medium undulating to carry that energy. If you hear a sound, the acoustic wave is propagating through the physical medium of the air molecules. A wave, by classical definition, is a disturbance within a medium. Therefore, if light is an electromagnetic wave traveling from the sun to the earth across millions of miles of seemingly empty space, there had to be a physical substance occupying that space for the light to wave through. Because you simply cannot have a wave of nothing. The scientific consensus demanded a medium. They termed it the luminiferous ether. They hypothesized it as an invisible, frictionless, weightless substance of infinite rigidity that permeated every single vacuum in the cosmos. And for Lorentz, the ether was not merely a placeholder. It was the fundamental bedrock of reality. It provided the absolute stationary frame of reference against which all motion in the universe could be measured. He vehemently rejected the idea of action at a distance. He could not accept that a magnet could attract a piece of iron across a vacuum without some invisible, physical mechanism connecting them. He desperately needed a universe of gears and levers, even if they were microscopic and invisible. He needed a constructive theory that explained the physical how, rather than just a mathematical formula that predicted the what. His entire psychological profile, that deep-seated need for absolute order and structural stability forged in the trauma of his childhood, found its ultimate expression in the concept of the ether. The ether was the ultimate, unchanging foundation. But the integrity of that foundation was about to be challenged by what is widely considered the most important failed experiment in the history of science: the 1887 Michelson-Morley experiment. The experimental logic was perfectly sound. If the universe is filled with this stationary ether, and the Earth is orbiting the Sun at roughly 30 kilometers per second, the Earth must be plowing through this ether. We should be generating an ether wind. Albert Michelson and Edward Morley designed an incredibly precise optical instrument called an interferometer, essentially an extraordinarily complex light splitter. They split a single beam of light. They sent one half of the beam traveling in the direction of the Earth's orbital motion, meaning it would be swimming directly against the hypothetical ether wind. They sent the other half of the beam traveling perpendicular to the motion. Then they reflected both beams back to a central detector. The physics assumption was that the light beam fighting against the ether wind would take fractionally longer to return than the perpendicular beam. When the two beams recombined at the detector, the slight difference in their arrival times would create an interference pattern, a specific shifting of the light fringes that they could measure. They were not messing around. They isolated their massive equipment on a block of sandstone floating in a pool of mercury to completely eliminate seismic vibrations. They rotated the apparatus. They measured at different times of day, at different times of the year. Their instrument was sensitive enough to detect an ether wind, a fraction of the speed of the Earth's orbit, and the data returned a null result, nothing. The light beams always arrived back at the exact same time. The speed of light remained completely constant, regardless of the direction the Earth was moving. They found absolutely zero evidence of the ether wind. That null result plunged the theoretical physics community into an existential crisis. The mathematics of Maxwell required a medium, but the empirical data of Michelson and Morley denied its existence. It created an irreconcilable paradox. If there is no ether wind, either the Earth is perfectly stationary at the absolute center of the universe, which violates centuries of Copernican astronomy, or the fundamental understanding of wave propagation was fatally flawed. When Lorentz confronted this paradox, he did not abandon the ether. He doubled down. He attempted to mathematically contort the physical universe to explain why the ether was there, yet perfectly hiding itself from the interferometer. The mathematical gymnastics he performed were nothing short of brilliant, even if the underlying physical premise was flawed. Lorentz analyzed the Michelson-Morley apparatus and proposed what we now know as the Lorentz contraction. He suggested that when physical matter moves through the ether, the electrostatic forces binding the molecules together are physically compressed by the ether wind. He asserted that the physical arm of the interferometer actually shrinks in the direction of its motion. He calculated the exact mathematical factor by which it would shrink, the gamma factor, which is 1 over the square root of 1 minus the velocity squared over the speed of light squared. And he didn't stop at physical length. He realized that to make the math balance perfectly, he also had to manipulate time. He introduced the concept of local time, theorizing that a clock moving through the ether ticks at a slightly slower rate than a clock at rest. He looked the scientific community in the eye and told them, the reason Michelson and Morley couldn't measure the ether wind is because their measuring stick physically contracted, and their physical clocks ticked slower by the exact mathematical proportion required to perfectly cancel out the measurement of the wind. He constructed a theoretical model where the ether exists, but the laws of physics contrive to make it fundamentally undetectable to any observer moving within it. The preeminent French mathematician, Henri Poincaré, issued a devastating critique of Lorentz's model. Poincaré did not hold back. He pointed out that this was essentially an ad hoc hypothesis, a convoluted excuse invented solely to save a dying theory. Poincaré's critique struck at the mechanical heart of Lorentz's theory. He applied Newton's third law of motion. For every action, there is an equal and opposite reaction. In Lorentz's framework, the ether exerts a physical force on matter, compressing the yardstick. However, Lorentz simultaneously insisted that the ether was completely immobile and unaffected by matter. Poincaré argued that a one-way physical interaction is mathematically and physically impossible. Furthermore, Poincaré analyzed Lorentz's model of the electron itself. If the electron is a tiny sphere composed entirely of negative electrical charge, the repulsive forces of that charge should blow the sphere apart instantly. To prevent his theoretical electron from exploding, Lorentz was forced to adopt a concept suggested by his critic, Poincaré pressure. This proposed the existence of an unknown, non-electromagnetic inward pressure, perfectly counteracting the electron's outward repulsion. The mechanical complexity was becoming absurd. To maintain the ether, Lorentz was layering unprovable forces on top of fictitious fluids carrying electromagnetic momentum, which sets the stage perfectly for 1905. We shift from the established titans of European academia to a 26-year-old patent clerk sitting in an office in Bern, Switzerland, Albert Einstein. Einstein looked at the tangled mess of Poincaré pressures, fictitious fluids, and invisible contracting yardsticks. And he looked at the perfect, pristine mathematics that Lorentz had derived to describe the contraction and the time dilation. Einstein achieved a breathtaking conceptual breakthrough. He took Lorentz's exact mathematical equations, the Lorentz transformations, and violently stripped away all of the mechanical scaffolding. He cut it all down. He realized that you do not need the ether. You do not need molecular compression. You do not need Poincaré stresses. Einstein proposed special relativity. He declared that the speed of light is simply a universal constant for all observers, regardless of their relative motion. And because the speed of light is constant, space and time themselves must be flexible. The yardstick doesn't physically compress because it's grinding against invisible ether jelly. The actual geometry of space-time changes depending on your relative velocity. Einstein shifted the framework from dynamics, the study of underlying forces in physical materials, to kinematics, the study of pure motion and geometry. He discarded the physical medium entirely and replaced it with a mathematical relationship. Occam's razor strongly favored Einstein. His theory was elegant, clean, and required far fewer assumptions. Why then did Lorentz, a man possessing the raw intellect to derive the mathematics of relativity before Einstein even published, absolutely refuse to accept Einstein's interpretation? The divide between them was fundamentally epistemological. They disagreed on the ultimate purpose of theoretical physics. Einstein had constructed a principle theory. He started with overarching postulates and mathematically deduced the consequences. It tells you exactly what the clock will do, but it doesn't tell you how the gears are turning to make the clock do it. Lorentz demanded a constructive theory. He required a model built from basic physical elements, particles, fields, forces, that interacted to produce the macroscopic result. For Lorentz, telling him that space and time are relative was an abandonment of physics. He required a substantial reality. Even if the ether was permanently undetectable, its conceptual existence provided the necessary physical seat for electromagnetic fields. He could not accept a universe composed of empty mathematical voids. They were staring at the exact same differential equations, but they were interpreting them as two fundamentally different realities. Yet, their personal dynamic is astonishing. You would expect a bitter, lifelong feud between the old guard defending his territory and the young radical tearing it down. But they engaged in rigorous, uncompromising intellectual debate, while maintaining a profound personal affection. Einstein revered him. In his later letters, Einstein described Lorentz as the greatest and noblest man of our times, literally calling him a living work of art. When Einstein traveled to Leiden, he stayed in Lorentz's personal home. Lorentz treated him like an intellectual son. Einstein recognized a fundamental truth. His own revolutionary leap was only possible because Lorentz had spent decades building the springboard. But a rigorous historical analysis requires us to strip away the hagiography. When historians like Fritz Behrens combed through the administrative records of the early 20th century, the flawless image of Mr. Perfect began to crack. The archives reveal a deeply problematic pattern of behavior: the nepotism controversy. The man who demanded absolute objectivity in his physics was leveraging his immense personal influence to install his children into comfortable academic careers. His daughter, Gertruida, was undeniably a brilliant physicist who eventually married the prominent physicist Wander de Haas. However, Lorentz actively manipulated the system for her benefit. He secured lucrative translation contracts for her, and, in a move that completely violates academic ethics, he served as the direct supervisor for her doctoral thesis. The conflict of interest is glaring. A father cannot objectively evaluate his own daughter's doctoral defense. The pattern extends to his son, Rudolf, who showed no particular aptitude for the hard sciences. Yet, records show Lorentz utilized his leverage to secure prestigious librarian and administrative positions for Rudolf at the Taylor's Museum in Haarlem and the Royal Holland Society of Sciences. Crucially, Lorentz himself essentially directed the scientific operations of both institutions. He was placing his son on the payroll of organizations he directly controlled. While this appears deeply corrupt today, the socio-economic reality of the late 19th century Netherlands provides vital context. There was no modern social safety net. If a family member could not secure a livelihood, the financial burden fell entirely on the patriarch. Utilizing influence was often viewed as a fundamental familial duty within that cultural matrix. However, there is another incident in the archives where his influence had immediate, devastating consequences for a peer. A scientific debate that spiraled into catastrophic accidental sabotage. We must examine the records from the 1908 International Congress of Mathematicians in Rome. Max Planck had recently introduced a radical hypothesis to solve the ultraviolet catastrophe in black-body radiation. To make the math align with empirical data, Planck proposed that energy is not continuous. He hypothesized that energy is emitted or absorbed only in discrete, indivisible packets or quanta. Lorentz, the architect of classical continuous fields, fundamentally rejected Planck's discrete quanta. Lorentz was deeply anchored in classical thermodynamics, specifically the equipartition theorem, which assumed energy could be divided infinitely. So, in Rome, Lorentz stepped up to the podium for a highly anticipated plenary lecture and delivered a masterclass in classical physics, systematically and publicly dismantling Planck's quantum hypothesis. It was a rigorous, legitimate public peer review. The catastrophe lay entirely in the composition of the audience. Sitting in the lecture hall, absorbing every word of Lorentz's critique, was guest Hendrik Lorentz. He was a prominent Swedish mathematician, but far more importantly, he was a dominant, highly influential voice on the Nobel Prize Committee. And the archives reveal a heartbreaking secret. The Physics Committee had already initiated the process to award the 1908 Nobel Prize in Physics to Max Planck. The wheels were already in motion. Hendrik Lorentz listened to the most respected physicist in the world declare that Planck's foundational theory was mathematically invalid. Convinced by Lorentz's unquestionable authority, Hendrik Lorentz returned to Sweden, forcefully campaigned against Planck's nomination, and single-handedly derailed the committee's decision. Max Planck lost the 1908 Nobel Prize directly as a result of Lorentz's speech. You would assume that a sabotage of that magnitude would generate a lifelong, bitter vendetta. How did Planck react when he discovered the man who had cost him the ultimate prize? The very day after the Nobel Committee announced their final decision, awarding the 1908 prize to Gabriel Lippmann instead of Max Planck, Planck boarded a train. He traveled directly to Leiden, the hometown of the man who had just cost him the prize. But he did not go to confront him. The historical sources confirmed that Planck went to stay as a guest in Lorentz's house. They sat down, they shared meals, and they continued their mathematical debates. It is a profound testament to the emotional and intellectual compartmentalization of both men. Planck recognized that Lorentz's critique in Rome was aimed entirely at the differential equations, not at Planck's personal character. They possessed the impossibly rare ability to separate their fierce theoretical disagreements from their deep personal respect. And that specific trait, the ability to act as an objective, depersonalized mediator, navigating massive egos and conflicting theories, is exactly what elevated Lorentz from a brilliant physicist to a geopolitical savior for the scientific community. This brings us to the monumental Solvay conferences, the institutionalization of international physics. Ernest Solvay was a massively wealthy Belgian industrialist who had made a fortune refining sodium carbonate. But Solvay harbored eccentric, highly flawed amateur theories about gravity and matter, and he wanted the greatest minds in the world to validate them. So, he funded an unprecedented international summit in Brussels in 1911. He invited Albert Einstein, Marie Curie, Max Planck, Ernest Rutherford, and Henri Poincaré. To manage this room of monumental egos, Solvay selected Lorentz as the chairman. Looking at the transcripts of the 1911 conference, the choice was obvious. Lorentz wasn't just mathematically superior. His diplomatic and linguistic skills were unmatched. The linguistic barrier was a massive hurdle in early 20th century science. You had Einstein presenting complex thermodynamics in German, Poincaré arguing in rapid-fire French, and Rutherford, speaking heavily accented English. Lorentz was flawlessly fluent in all three. The transcripts show Lorentz actively translating between the scientists in real time, clarifying conceptual misunderstandings, softening aggressive critiques, and keeping the focus relentlessly on the physics. Einstein later wrote that Lorentz guided the conference with incomparable tact and unbelievable virtuosity. The 1911 conference proved that international scientific collaboration could rapidly accelerate discovery. But then, the geopolitical reality shattered the academic ideal. The outbreak of World War I in 1914 completely fractured the European scientific community. The trauma of the First World War destroyed the illusion of objective, borderless science. In 1914, 93 prominent German scientists and intellectuals signed the Manifesto of the 93, explicitly defending the German military invasion of Belgium and adopting a fiercely nationalist stance. It outraged the Allied scientific community. Following the armistice, French, Belgian, and British scientists instituted a strict, unforgiving boycott. They refused to publish in German journals. They refused to cite German papers. They absolutely refused to sit in the same room as a German scientist. They referred to the Germans as the banished. The international engine of physics ground to a violent halt. Half of the quantum revolution was happening in Germany, and the other half of the scientific world refused to even look at the math. This is where Lorentz stepped out of the laboratory and into the role of international statesman. The geopolitical positioning of the Netherlands was vital here. The Dutch had maintained neutrality throughout the war. Therefore, Lorentz, as a Dutchman, possessed the rare credibility to speak to both factions. He utilized the newly formed League of Nations, specifically the International Committee on Intellectual Cooperation, to begin the grueling work of diplomatic reconstruction. His correspondence from this period shows him essentially running shuttle diplomacy. He wrote agonizing letters to the French Academy of Sciences, pleading with them to recognize that the laws of nature are not French or German. He urged the German scientists to issue statements walking back their wartime nationalism. He leveraged every ounce of his personal prestige to force a reconciliation. His argument was deeply philosophical. He believed that the pursuit of scientific truth was the highest expression of human civilization, and to allow temporary political borders to impede that pursuit was a betrayal of their intellectual duty. His relentless diplomacy culminated in the legendary Fifth Solvay Conference of 1927. The 1927 conference is immortalized in what is widely considered the most intelligent photograph ever taken. You see the attendees gathered outside the Institute of Physiology in Brussels. Marie Curie is in the front row. Einstein, Bohr, Heisenberg, Schrödinger, Pauli, Dirac. 17 of the 29 individuals in that single frame were, or would become, Nobel laureates. But the true historical weight of that photo isn't just the density of genius. It is the fact that the Germans are in the frame. Lorentz successfully broke the boycott and brought the German physicists back into the international fold. The scientific ramifications of that diplomatic victory are immeasurable. The 1927 conference was dedicated to the newly formulated quantum mechanics. It served as the battleground for the foundational interpretation of reality itself. If Lorentz had failed to bring the Germans, specifically Werner Heisenberg and Max Born, to Brussels, the conference would have been entirely hollow. By forcing them all into the same room, Lorentz facilitated the legendary Einstein-Bohr debates. We have Einstein, horrified by the implications of Heisenberg's uncertainty principle, arguing desperately for a deterministic universe, famously insisting that God does not play dice. And we have Niels Bohr, arguing for the Copenhagen interpretation, asserting that the universe is fundamentally probabilistic, existing in a superposition of states until observed. Lorentz presided over this intellectual earthquake, and the ultimate agonizing irony is that Lorentz fundamentally agreed with Einstein. Lorentz still yearned for a deterministic, mechanical universe. He was deeply uncomfortable with the probabilistic chaos of quantum mechanics. Yet, his commitment to the scientific method was so absolute that he dedicated his twilight years to ensuring that the proponents of the new physics had a platform to tear down his classical universe. He mediated the birth of a reality he did not entirely believe in. It is the ultimate act of intellectual selflessness. By the late 1920s, Lorentz had reshaped theoretical physics. He had predicted the fundamental components of matter. He had saved the international scientific community from geopolitical collapse. You would think he had earned a quiet retirement. But the Dutch government looked at this 65-year-old theoretical physicist and asked him to solve an immediate, terrifying crisis of civil engineering. We must examine the Zuiderzee project, the transition from the abstract, invisible world of subatomic particles to the brutal, kinetic reality of ocean hydrodynamics is astounding. To understand the stakes, we must look at the geography of the Netherlands, a nation effectively underwater, fighting a centuries-long war of attrition against the North Sea. In 1916, a catastrophic storm surge breached the dikes along the Zuiderzee, a massive shallow bay protruding into the heart of the country. The flooding caused immense economic devastation and loss of life. The government determined that the only permanent solution was to seal off the entire sea. They proposed building the Absolute, a colossal 30-kilometer-long dam stretching across the mouth of the Zuiderzee, effectively transforming a volatile saltwater bay into a docile freshwater lake. Constructing the physical barrier was daunting but feasible. The existential threat lay in the hydrodynamic consequences. The politicians and the populace of the neighboring coastal provinces, particularly Friesland, were paralyzed by a terrifying unknown. If you erect a 30-kilometer wall in the middle of a tidal system, where does the massive kinetic energy of the North Sea tide go? They were terrified that the water would reflect off the new dam, amplify the tidal waves, and cause catastrophic, permanent storm surges that would wipe out the coastal towns outside the enclosure. They needed absolute certainty regarding how the water would behave before they poured the concrete. The state committee tasked with calculating these tidal changes realized that standard engineering approximations were woefully insufficient. They required a mathematical model of unprecedented precision. And so, they approached Hendrik Lorentz to chair the committee. The optics of this decision are almost comical. They took a man whose entire career had been spent deriving differential equations about invisible electrons traveling through non-existent ether jelly, and they asked him to calculate the fluid dynamics of millions of tons of seawater. He had zero background in civil engineering, but the committee recognized his true capability. Lorentz possessed an unparalleled genius for modeling complex physical systems mathematically. He understood how to isolate the fundamental variables of an interacting system. He accepted the challenge, dedicating 8 years of intense, agonizing labor to a problem far outside his discipline. The engineering reports outline the specific mathematical nightmare he encountered. The primary obstacle was a phenomenon known as quadratic bottom stress. When a massive volume of shallow water flows through a channel, it drags against the topography of the seafloor. That friction dissipates the energy of the tidal wave. If the friction were simply linear, meaning if the water moved twice as fast, the friction doubled, the math would be difficult but solvable. However, fluid dynamics dictates that the friction is proportional to the square of the water's velocity. If the tide flows twice as fast, the drag is 4 times as strong. If it flows 3 times as fast, the drag is 9 times as strong. This creates highly complex, nonlinear, partial differential equations. The variables are constantly influencing each other in real time across the entire geography of the sea. In the 1920s, there were no digital computers. You could not run a simulation. Solving nonlinear equations of that magnitude analytically by hand was considered mathematically impossible. Lorentz looked at this impossible math and invented a workaround so elegant, it is still taught in hydrodynamic engineering today. It is called Lorentz linearization. He recognized that the engineers did not need to know the exact friction at every microscopic fraction of a second. They only needed to know the total energy dissipated over the course of a complete tidal cycle. So, Lorentz developed a mathematical technique to substitute the impossible nonlinear friction term with a manageable, artificial linear friction term. He approximated it, but with rigorous mathematical justification. He calculated a specific, custom coefficient for every distinct channel and bottleneck in the Zuiderzee. He designed these coefficients to ensure that his simplified linear equations consumed the exact same amount of theoretical energy over a full tidal cycle as the real quadratic friction would. He enforced an energy equivalence principle. He then divided the entire map of the Zuiderzee into a network of interconnected, one-dimensional channels. He established boundary conditions for where the channels met, and then he deployed human computers. He organized teams of calculators, individuals sitting in rooms for months, manually computing the massive matrices of linearized equations he had derived. To ensure absolute accuracy, he mandated that every single calculation be performed in duplicate by different teams. If the numbers deviated, they started over. The sheer administrative and mathematical discipline required was staggering. In 1926, the committee published its final report. Based entirely on his linearized mathematical model, Lorentz informed the Dutch government that their original design was fatally flawed. His calculations showed that the proposed alignment would dangerously amplify the tides near certain coastal towns. He instructed them to move the alignment of the dam further north, and he predicted the exact height the new tidal surges would reach. The government, placing their absolute faith in the aging theoretical physicist, altered the massive engineering blueprints based on his equations. The construction proceeded. In 1932, 4 years after Lorentz passed away, the final gap in the absolutic was closed. The engineers deployed their measurement instruments to record the new tidal reality. The recorded tidal heights matched Lorentz's manual. Linearized predictions down to the centimeter, it remains one of the most triumphant moments of applied mathematics in the 20th century. He proved that the highly abstract theoretical rigor he championed his entire life could be directly applied to alter the geography of his nation and protect the lives of hundreds of thousands of people. It served as the ultimate vindication of his belief in mathematical determinism. The universe, whether at the scale of the invisible electron or the macro scale of an ocean tide, obeys the equations. This sweeping narrative brings us to the end of the timeline. On February 4, 1928, Hendrik Lorentz died in Haarlem at the age of 74. The archival accounts of his funeral demonstrate exactly what he meant to the world. The response transcended the academic community. It was treated as a monumental national and international loss. The streets of Haarlem were lined with thousands of citizens. The procession was a state-like event. Sir Ernest Rutherford, representing the British Royal Society, spoke at the graveside. Albert Einstein stood in the crowd, openly mourning the man who mentored him, who debated him, and who mediated the birth of modern physics. But the single detail in the historical record that resonates the most, the one that perfectly encapsulates his legacy. At noon on the day of his funeral, the Dutch government ordered the suspension of the entire national telegraph and telephone service. For 3 full minutes, the communication grid of an entire nation went absolutely silent. 3 minutes of stillness to honor the mind that spent a lifetime mapping the invisible vibrations that connect the universe. It is a profoundly moving image, But as we close our examination of these archives, I want to leave you with a final analytical perspective on his defining controversy. For the last century, the narrative has framed Lorentz as a brilliant but tragic conservative. He is remembered as the dinosaur who refused to let go of the ether, the man who couldn't accept Einstein's elegant geometry of empty spacetime. He is remembered as the genius who stubbornly defended a ghost. Yet, if we examine the vanguard of theoretical physics today, that narrative begins to fracture. With the advent of quantum electrodynamics and the discovery of the Higgs field, modern physics insists that the vacuum of space is not empty at all. It is a bubbling, dynamic, substantial medium teeming with virtual particles and intersecting quantum fields. It is a physical structure that dictates the mass and behavior of matter moving through it. The empty mathematical void of relativity is essentially being replaced by a physical, interacting medium once again, precisely the kind of substantial, constructive medium that Lorentz demanded. So, the ultimate question history poses is this: was Lorentz actually a stubborn relic, clinging to an outdated 19th century error? Or did he possess an intuitive grasp of the universe's fundamental architecture that was simply a century ahead of its time, waiting patiently for quantum field theory to catch up to his ghost? Perhaps the invisible jelly wasn't completely wrong. It just evolved. If you are captivated by these deep historical contradictions, by the hidden truths and staggering intellects that engineer the reality we inhabit, please like, comment, and subscribe to Legendary Lives Unveiled. Share your thoughts on Lorentz's legacy below. We will continue pulling the archives and unraveling the truth behind the myths. Thank you for watching, and we will see you in the next one.